Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Steve Markham with us today. Hello, Steve.
Hey Frank, nice to be
Uh,
here.
well, it's good to meet you again. We actually did one in 2020, way back in the start of the pandemic. So you're one of a few who've done two of these. So very cool.
Fond
And
memories.
Steve, what is your geolocation these days?
I'm currently in Las Cruces, New Mexico, so it's my hometown. I'm at New Mexico State University. I'm actually at home currently because we had about an inch of snow today, which you're in Phoenix, right? So you
Yes.
know in the Southwest, we don't really have the infrastructure to handle it. So the university closed for the morning and the roads are all a mess because
Oh yeah, yeah.
like this much snow.
Very cool. Were you like born in Las Cruces?
Yep, born and raised.
Oh, very cool. Very cool. You're local. That's awesome. Very nice. And you like butterflies, I take it. You got some nice butterflies there on your.
Well, my 2-year-old daughter likes butterflies. I
Ah,
like them too,
you
but they're
like them
most
too. You like your daughter.
yeah.
Very cool. Very, very nice. Um, let's see. And Steve, what do you like to do for research?
So my research, generally speaking, focuses on sort of the interconnection between what is typically thought of as an atmosphere and what's typically thought of as an interior of planets. So the intellectual tradition between both of these sort of have different histories. So with atmospheric dynamics, a lot of it comes from meteorology and oceanography. And with the interior science, a lot of it comes from geophysics or stellar physics
Yes.
and disciplines like that. So what we're noticing as we see planets in the outer solar system and also exoplanets is that there is sometimes quite a lot more coupling between these two systems that are quite decoupled in the Earth. And so a lot of my research focuses on understanding how they interact with each other.
Very cool. Very cool. And that is going to bring us to this very awesome PSJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Stable stratification of the helium rain layer yields vastly different interiors and magnetic fields for Jupiter and Saturn. And Steve, take us away.
All right, so this is work I did together with Tristan Guyot at the Nice Observatory. Part of the work was done at Nice Observatory, and part of it was done at New Mexico State. And the general idea is to try to take a sort of lessons that we've learned from atmospheric dynamics and apply them to interior science on Jupiter. And specifically, we're interested in understanding the dynamics of the helium rain layer from the perspective of sort of fundamental fluid dynamics and fundamental thermodynamics to sort of answer the decades-old question, first posed in the 1970s by Dave Stevenson, of what do we expect to be the dynamical state of this helium rain layer?
Cool.
So I want to back up just a little bit for those who may not be super familiar with what I mean by a helium rain layer. It sounds sort of like an absurd idea. And the general idea here goes back to the early days of quantum mechanics in the 1930s,
Mhm.
and in particular by Wigner and Huntington in 1935,
Okay.
that predicted the metallization of hydrogen at high pressures. So if you look at the location of hydrogen on the periodic table, you see that it's in the same column as all the alkali metals. And
Yep.
what they have in common is that they have one valence electron.
Mhm.
Yet we experience hydrogen behaving as a neutral diatomic gas in everyday experience, while these other metals are metals. So why is that? What's the difference? So generally speaking, a metal will exist as sort of a lattice of ions with electrons being shared by all of these ions in what's called a Fermi gas.
Yes.
The idea is that ordinarily, if you're at low pressures, these hydrogen atoms are going to want to bond to each other in order to share their valence electrons, in order to have a filled outer shell. And each of these molecules are sort of independent from each other, and they're well described from the kinetic theory of gases and stuff like that.
Cool.
However, as you go to higher and higher pressures, you're essentially forcing these protons closer and closer together. And so the distinction between each of these individual atoms becomes less and less meaningful.
Yep.
And they eventually there's a sort of gradual transition towards a metallic type of behavior, where you instead have kind of a soup of protons that are all sharing electrons,
Yes.
and then they begin to behave as a metal. And under the thermodynamic conditions relevant in Jupiter, they behave like a liquid metal.
Okay.
This is especially interesting because it's able to drive a dynamo to create the magnetic field on Jupiter.
Uh-huh.
So this is all of sort of fundamental importance.
Cool.
Uh, Now, the aspect that is relevant here is that if you form a metal out of hydrogen, what happens to helium? Because in general, for the in the cosmos and in a planet like Jupiter or Saturn, you have hydrogen and helium both coexisting.
Yep.
As molecular gases, they're able to coexist in any mixing ratio. It's because they're just sort of billiard balls in the kinetic
Right.
theory sense. However, as this hydrogen begins metallizing, because helium is a noble gas, it actually has the highest ionization energy of any element. And
Yes.
so you need to go to much higher temperatures in order to ionize helium. And so neutral matter doesn't like to be embedded into sort of a metal. It's energetically unfavorable. So
Yes.
what actually begins to happen is that you have a phase separation between the metallic hydrogen and the helium.
Nice.
And so the question that we are sort of interested in here is why are Jupiter and Saturn's magnetic fields so different when we think that they're both governed by sort of similar interior dynamics?
Okay.
We expect both of them to have this phase separation happening. The
Yep.
Galileo probe measured depleted helium and neon in the atmosphere of Jupiter, which
Yes.
conclusively sort of proves that there is this phenomenon going on in Jupiter. We believe it's happening in Saturn as well. But if both planets are sort of governed by the same physics, how come their external magnetic fields are so different? And to
Okay.
explain a little bit what I mean, Saturn's magnetic field is completely axisymmetric and spin
Yes.
axis aligned within zero point 0.1 degrees of the spin axis.
Yes.
And if there is any non-axisymmetry in Saturn's magnetic field, it's practically undetectable based on what we were able to measure from Cassini.
Yes.
Whereas Jupiter has a very complex non-axisymmetric structure. So what's going on here? So just
Good
to skip
question.
ahead to the answer we're going to propose,
Okay.
we have figure 6,
Let's get it.
which is the last figure in the paper, and it's just sort of a cartoon that I drew to sort of illustrate the differences between these. And we're going to argue that Jupiter may have a thin helium rain region,
Okay.
while Saturn has a thick helium rain region.
Mm,
And and the idea is that on Jupiter, this thin helium rain region can be very thin, on the order of tens of kilometers potentially.
okay.
Whereas on Saturn, it can be much thicker. Constraining exactly the thickness is a little bit complicated, and I'll explain why as we go through the paper. But this is the general idea. So the explanation for the external magnetic fields could simply be that while the same thing is happening on both planets, the differences in thickness is important for regulating their external magnetic fields.
You said tens of meters for the Jupiter, and what is the
Sorry,
approximately
tens of kilometers, and they've said
tens of kilometers.
tens of
And
kilometers.
what is it for Saturn? Hundreds?
For Saturn, it could be thousands of kilometers. It
Thousands.
could be
Okay.
it could be adiabatic or even subadiabatic. Whereas
Okay.
on Jupiter, we expect it to be highly superadiabatic.
Yeah.
And so yeah, I'll explain a little bit why.
Okay.
Um, so sort of again stepping back and sort of the part of the reason that I did this work originally with Tristan is because came up with this idea in the 90s that he called a convective inhibition by moist convection
Yes.
that he originally applied to Uranus and Neptune to make sense of some Voyager data. And the way to understand this idea of convective inhibition, we need to sort of think about what convection is fundamentally. So
Yes.
fundamentally, sorry, did you have a
No,
question?
no,
Okay.
no. Anytime someone says convection fundamentally, I go, oh, okay.
Uh-oh, yeah, we're in for it
Here we
now.
go.
Um, so if you have a homogeneous fluid, then
Okay.
you will use what's called the Schwarzschild criterion, which for a low viscosity fluid essentially amounts to asking, is it adiabatic or superadiabatic
Yeah.
in an atmosphere? So in an incompressible fluid like water, that basically means is there going to be a temperature gradient or zero temperature gradient. In the atmosphere, it's a little more complicated because there are compressibility effects, but that is essentially what it boils down to.
Okay.
However, if there's more than one species present, so if there's a compositional gradient, then
Yeah.
in stellar physics, you would normally invoke what's called the Ledoux criterion,
Yep.
which takes into account the compositional gradient that affects the density. So the idea is that if you have a compositional gradient, so denser stuff like helium-rich stuff underneath more hydrogen-rich stuff. So, like for example, in a star, if there's fusion occurring that can introduce a compositional gradient,
Right.
then you can sustain a super adiabatic temperature gradient
Yes.
so long as it is accommodated by the compositional gradient.
Okay.
So the concept of convective inhibition is sort of one way of looking at it is a special case of the Ledoux criterion,
Okay.
where the compositional gradient and the temperature gradient are actually coupled to each other.
Okay.
And to understand how this may arise,
Mhm.
the way I like to think about it is just imagine you're on a beach. We both live in the desert, so of course this is difficult for us
It's a
to
dry
imagine
beach,
in
but
daily
okay.
lives. But I was in Nice before this, so there was an ocean there. So imagine that you're on a beach on a sunny day on a planet like much like the Earth, but you replace the atmosphere instead of with nitrogen, as is primarily what Earth's atmosphere is made of, you replace it with hydrogen.
Okay.
So
Okay.
now, if you have warm material on the Earth, if you have warm material immediately over the ocean surface, that warm material is going to rise. Heat rises because it expands from like an ideal gas, and that causes it to be positively buoyant and float towards space to sort of get rid of that heat, and
Yeah.
that drives convection.
Yes.
And
Source.
one thing that we don't usually think about that is relevant is the fact that a water molecule is a lower mass than a nitrogen molecule. So if you have water vapor that enters this parcel of expanding warm gas,
Oh,
it's a small correction, but it doesn't really matter. If anything, it's just going to make it even more buoyant.
yes.
And it's in terrestrial meteorology, it's a correction that you have to take into account if you're doing things carefully, but it's not quite of fundamental importance. The mass relationship between nitrogen and water, we don't really think about it that much. But
Okay.
now think again about the planet with the hydrogen atmosphere.
Yes.
Now the water molecule is substantially heavier than the hydrogen molecule.
Yes.
And so if you have a warm parcel of gas that's right above the sea, then as it warms up, yes, it expands, the molecules get further away from each other, but it also allows more water vapor to enter the parcel. And
Yes.
so it changes its composition.
Cool.
So the idea behind moist convective inhibition that Tristan first pointed out, and now it's been worked on by other people like Jeremy LeConte, Jim Friedson, Erica Gonzalez, myself, and others. But the general principle is essentially that now as you continue to increase the temperature gradient by making it hotter and hotter at the surface,
Okay.
you're
Okay.
simultaneously increasing the compositional gradient.
Yes.
And because the density scales as one over the temperature. But the amount of mixing of water vapor that can mix in behaves like a saturation vapor pressure, which is an Arrhenius relationship, which is a
Uh,
much steeper function of pressure,
yeah.
sorry, of temperature. There's a turnover point where the compositional effect will always win against the temperature effect.
Okay.
So in
Okay.
the traditional way of thinking about the Ledoux criterion, you
Yeah.
just make the temperature gradient steeper and steeper until it's so steep that it drives convection. In the sort of Guyot criterion, which I like to call it, but Tristan doesn't like it, but I'm going to call it that anyway. The temperature gradient is now actually coupled to the compositional gradient. So you can
Right.
try to make the temperature gradient steeper to drive convection, but by doing that, you're also making the compositional gradient steeper,
Yes.
therefore getting yourself further and further away from an instability.
Mm-hmm. Mm-hmm.
So what has been shown by some of the authors I mentioned previously is that if you do a linear stability analysis on this type of system, you find that it's stable against not only ordinary sort of overturning convection, but also other forms of convection like double diffusive convection and
Or useful.
semi-convection
Yeah.
and other
Yeah.
things
Yeah.
that are relevant in oceanography.
Uh-huh.
So traditionally, when confronted with this simultaneous compositional and temperature gradient that we expect to be present in these Jovian planets,
Okay.
this sort of assumption of double diffusive convection is what's used by interior and evolution models. So people like Nadine Nettleman and Chris Mankiewicz, just to name a
Yes.
few, have recently done models along those lines.
Uh-huh.
However, if we ask the question of whether this idea of moist convective inhibition is relevant to this system, then we can perhaps have a more rigorous prediction for what we expect this behavior to be like.
Yes.
And so that was the motivation to do this. People kept asking me if this idea could happen for the hydrogen helium system, and I kept saying no. But eventually, I just went ahead and
Oops.
tried the calculation, and I surprised myself and found that it actually does work.
Cool.
Um, Okay, so that was sort of the intro spiel. I'm sorry if that went a little long.
That was awesome. That was fantastic. You put some
That's
real
just sort of, it's on the
context to it.
introduction of the paper, more or less.
Yeah. Well, it's so much nicer to hear from you. Okay. So where do you want to go? You want to talk about some stability of the brain layer?
Yeah, so in a prior publication, Tristan, Dave, and I defined this parameter that we call the effective coefficient of thermal expansion. So that's equation 3, and it's related to equation 1, which is the classical
Traditional.
coefficient of thermal expansion.
Correct. Yes.
So the classical coefficient of thermal expansion is defined, by definition with a unitary substance.
Yeah.
So it's just the amount that the density changes with temperature, and it's a dimensionless, or no, it has dimensions of 1 over temperature.
Yes.
So the effective coefficient of thermal expansion is sort of generalizing this idea by adding an additional term that just takes into account how the composition also is a function of temperature, just like I was talking about before.
Yes.
So if you plug in an Arrhenius relationship, so
Very
just a
cool.
few lines down, I have P saturation is proportional to
Yep.
the exponent of the
Yep.
minus of the latent heat over RT.
Mm-hmm.
So this is how sort of ideal gases in coexistence with liquid vapor behave. But in general, it can behave much more in much more general
Complicated.
ways.
Yeah.
And so in order to understand that behavior, we use data from Schottler and Redmer, which is shown in figure 1.
Okay, let me just finish that. Okay, I'm with you. Figure 1. Okay. Let's do some coexistence curves. Bum, bum, bum.
Indeed. So these are from ab initio quantum mechanical simulations from Schottland and Redmer for the hydrogen helium, the hydrogen helium system.
Mm-hmm.
And the way to read this is that you take a given temperature, which is the temperature that you are ambiently at,
Yep.
and you take a given pressure. So here are some individual curves from that paper that show what those curves
Mhm.
look like as a function of composition. So here we have Y, the mole fraction of helium on the
Yep.
y-axis, on the x-axis, and
Yep.
then temperature on the y-axis. Um, so the way to read this is, okay, so you're at a given pressure, so you pick one of these curves. Really, it's a two-dimensional surface, but you can pick one of the curves if that pressure corresponds to the pressure of interest, and then you can pick a given temperature. So let's say the 4 megabar curve at 8,000 Kelvin.
Okay.
You see that if you drew a horizontal line, you would intersect at 2 points, and that basically tells you that there are going to be two coexisting phases of those compositions. One is going to be hydrogen rich, and one is going to be more helium rich.
Very
And
cool.
that's sort of the fundamental aspect of helium rain. But if you look again at equation 3, allowing ourselves to have these curves and particular their gradients allows us to solve that equation if we given that data.
Mm-hmm.
Um,
Okay.
so that's essentially what we do, and we use that to calculate the effective coefficient of thermal expansion,
Mm-hmm.
um,
Okay.
which is shown in figure 3, I believe.
Okay, I'm with you. I'm good. We got two solutions, and figure 3 is our effective coefficient. Yes.
Yes. So this is sort of I would say the primary finding in terms of science. After this, I'll talk about like sort of preliminary ideas about how this should affect the interiors of Jupiter and Saturn. But this is the sort of main science result, I would say.
Cool.
And what it shows is just a computation of the effective coefficient of thermal expansion given this data and given a suitable equation of state. We use one from Saburo Howard
Okay.
and Burkhard Militzer.
Okay.
And in order to calculate these quantities, we just use equation 3. And what we've done here is we've shown sort of in
Yes.
pressure temperature space how we expect the behavior to be. So sort of below what we call the condensation curve, you have
Yes.
fully demixed entities. So you'll have you'll have pure helium and pure hydrogen completely unmixed. Now above what we call the critical curve, or is
Okay.
generally called the critical curve, you can mix in any proportion.
Yeah.
And so if you think back to figure 1, that basically just means you're above the maximum point of those curves. And
Yes.
so you don't intersect the curve at all, and any composition is allowed.
Yes.
Now, in these intermediate regions, you have these curves of constant composition that go through them. So they sort of imply a composition of the hydrogen that the hydrogen-rich phase.
Okay.
And so going up towards the critical curve, it's going to be about a 50-50 mixture or close to it. It depends on the specific shape of those curves. In the lower limit, the condensation curve, it's going to be 0% helium. And then in these intermediate regions, you have different quantities of helium. So this solid curve corresponds to a protosolar helium abundance. And then
Okay.
the dashed curve corresponds to so the bottom dash curve corresponds to the measured helium abundance from the Galileo probe, and
Okay.
then the dash curve above it is the corresponding, based on mass conservation, expected helium abundance of sort of the deep interior that has more helium in it. And then these dotted curves are much more speculative because Saturn's helium abundance actually hasn't been measured directly.
Right.
But we can speculate based on what we think we know about the phase diagram, what we think it might be. And so then you have these corresponding dotted curves of a helium enriched deep interior in Saturn and a helium depleted envelope.
Cool.
And then we've also drawn the different published interior models for Jupiter and Saturn
Yep.
and see where they intersect these curves.
Yep.
And the main finding is that the details don't actually matter that much, because what we find is that sort of all over parameter space, with the exception of some of these low pressure areas at around 1 megabar where we've hatched out these regions where
You start.
where the effective coefficient of thermal expansion is positive, and so you expect convection to operate like normal.
Mhm.
But in the regions around in this plot 2 megabars, although whether that's the correct area is debatable, and we'll talk about that more later. But in this figure, around 2 megabars, you have where we actually expect these interior profiles to intersect
Yes.
with these curves of constant composition
Cool.
that correspond to the envelope composition of these planets. And at that point, you
Cool.
see that there's a color. So it's like green. And so that means some kind of negative coefficient of thermal expansion.
Uh-huh.
And interestingly, the order of magnitude is similar to what the positive effective coefficient of thermal expansion would be. So it basically inhibits convection just as efficiently as a normal
And
coefficient of thermal expansion would drive convection.
very cool.
Is one way to think about it, although that's a little bit imprecise. Anyway, so
It's
what
very
we
intuitive. Okay.
so what we essentially predict is that is that the helium rain layer on both Jupiter and Saturn should be stable against both ordinary and diffusive convection.
Okay.
And so in the paper, we go a little bit into the numbers and specify like what conditions are necessary. But based on taking numbers from previous authors who have thought about some of the microphysics and some of the diffusive dynamics and kinetics more seriously, we think that it's overwhelmingly plausible by more than 4 orders of magnitude that it should inhibit all of this stuff.
There you go. Not even close.
So we're talking about a stably stratified
Yes.
region in Jupiter and Saturn.
Yes.
Um,
Very.
so I began by sort of talking about the magnetic fields. And so if you go to figure 2, we can talk about why that's of interest.
E fields.
So yeah, right there.
Uh-huh. Just getting it centered. There we go. Nice.
Yeah, so this basically shows kind of what the open problems are. And so there's kind of a lot going on in this figure. So I'll just walk through it. On the left side, y-axis, we have temperature. And on the right side y-axis, we have electrical conductivity. I'll talk about why that's important in a minute.
Right.
And then the x-axis on the bottom, we have pressure. And then on the top, we have radius.
Yeah.
So Jupiter fractional radius,
Yeah.
just to get a sense of where all these
Where it's
all these things connect to each other.
Uh-huh. Good.
And the observation that in part motivated this work was from Connerny et al. So this is a major result from the Juno mission studying the magnetic field. Jack Connerny and others put what's called a Lowe's radius on Jupiter's magnetic field spectrum. And this is an unexpected and in some sense fantastic result because the Lowe's radius on the Earth corresponds almost precisely to the location of the core mantle boundary. And what the Lowe's radius is
Okay.
essentially a location where if you take the full magnetic power spectrum of the Earth and you take the different spatial scales of the different spherical harmonic coefficients
Huh?
that correspond to it, you essentially find that large scales have more power and smaller scales have less power. And the one explanation for why that could be is essentially that the dynamo is all generated in the liquid iron core, and that as it truncates in the mantle, which is solid and insulating, then at that surface of the core mantle boundary,
Uh,
perhaps there's equal power in all sizes.
got it.
And
Got it.
but because of geometric attenuation, just from classical field theory,
Yep.
through an insulator, then the lower spatial scale coefficients sort of attenuate with space as they travel the distance through the
Hmm.
insulating mantle.
Okay.
And so, so you find that that radius for the Earth corresponds precisely to the core mantle boundary. What was surprising is that the behavior of Jupiter matched this Lowe's spectrum almost exactly.
Wow.
And so it turned out to be a really good model. Now, the reason that this is surprising, it comes to from this electrical conductivity that you see on the right-hand side
Yeah.
y-axis. And
Mm.
there's the corresponding green curve that you see basically it increases monotonically and linear. So this is a linear scale, not a log scale,
Uh-huh.
with pressure and temperature.
Uh-huh.
As you follow the adiabat of Jupiter down into its interior.
There.
So why then should there be such a well-behaved truncation of the of the magnetic field as if it behaved like the Earth? Because
Yeah.
if it were a fully convective body, um, and then why should there be some well-defined radius where this behavior exists? On the Earth, there's a theoretical heuristic for why this should be. On Jupiter, it's less clear.
Yeah.
Now, what Jack Connerny invokes is essentially this helium rain layer and says if it's stable against convection, then that could act as a natural truncation point.
Yeah.
There are some complications with that, especially that I can get into more when we talk about potential future work. But that was sort of the motivation here. So if it is true that Jupiter's magnetic field is giving us information about the helium rain layer,
Hmm.
then what type
Yeah.
of information does it give?
Right.
And this sort of shows why this is such kind of a fraught problem right now. And that's because there is not a consensus among the community about what the phase diagram of this hydrogen helium system should look like.
Mm.
There is a consensus that at sufficiently high pressures, they will indeed phase separate. So there's some wonderful experimental work from Brigoux et al. 2021 that actually claims to demonstrate this phase separation in a laboratory
All right.
um, using shock experiments.
Uh-huh.
And then the remainder of these sort of purple curves are all ab initio quantum mechanical simulations.
Okay.
And what you see is that this Brigoux et al. Curve is markedly divided from these computational simulation curves, and also that the computational simulation curves do not overlap very closely either.
Yeah.
I mean, these are if you look at, for example, this the circular points from the Lawrenson et al.
Lorenzen. Uh-huh.
Paper and compare
Uh-huh.
it against the Schottler and Redmer paper,
Right.
that's like a 4,000 Kelvin difference at a given pressure level. So that's quite significant.
Quite a bit.
So what we're hoping, so this is just a little bit of additional context and motivation for why we're interested in understanding what we really expect the physical behavior of this helium rain layer to be, so that we can maybe start making some statements about how we might expect it to affect the magnetic field.
I'm with
Um,
you. Good. I'm with you.
okay, so the helium rain layer is stable. It's related to the magnetic field. What kind of interiors are we expecting to see? So I believe that brings us to figure 4, if I'm remembering the order of figures correctly.
Stability, convection, structure of the rain layers. And yes, figure 4 is PTs.
Yes. Okay. So I want to comment for a minute just because I just showed that previous figure. Why did we use Schottler and Redmer's phase diagram?
Okay.
There were other phase diagrams to choose from.
Yeah.
The reason essentially is that it covers three-dimensional parameter space, pressure, temperature, and composition that
Good.
allows us to use it fully generally.
Okay.
However, in some sense, we know it must be wrong, and to understand why would be to go back to the previous figure. Maybe we don't have to, but if you look at where the okay, yeah. So if you look at this from Howard, et al. 2023, this thick black curve, which
Yes.
shows the expected temperature pressure profile of Jupiter. And then you see the coexistence curve from Schottler and Redmer 2018. You see that
Okay.
they actually never cross.
No, they don't.
But we have the Galileo measurement that shows that helium rain must be
Must
occurring. And
be
so we know that it's wrong. Nevertheless, we have to use it anyway. Because it's the equation of state we have that has the densest sort of coverage in three
right.
dimensions,
Right.
but we must modify it in some way. So sort of following
Okay.
the work of Minkovich and Fortney from 2020,
Yes.
we choose to sort of just translate the curves around
I was
pressure
going
to
to say,
space.
just move them.
And it's a completely ad hoc decision.
Yeah.
It's not based on any physical argument, besides the fact that we have an observation that Jupiter's envelope is depleted in helium. So we know that something has to be done to this phase diagram.
Right.
And in the appendix, I talk more about how difference in Appendix A, I talk more about how this can affect potentially our conclusions.
Okay.
And to summarize, we think that our conclusions are robust, even
Okay.
given these uncertainties.
Okay.
But these uncertainties also show that there can be differences in the behavior and placement of the helium rain layer, which brings us back to figure 4. Sorry to make you keep jumping around.
No, it's fine. It's perfectly fine. It's great. It's good. Okay. So now we got that down. Okay. Figure 4. Now we get into the PT structures. Okay.
So these diagrams basically take two different assumptions about what uh, how to translate these curves from
Oh,
Schottler and
okay.
Redmer.
All right.
So the
Sure.
first curve sort of puts it 200 Kelvin up, and
Yep.
then about half a megabar to the left. And then that gives you an intersection point between an adiabat that is extrapolated down to up to the atmosphere, where we have Galileo measurements of the temperature and pressures to give us a sense of where we are in terms of
Mhm.
entropy. So if you have an isentropic or equivalently adiabatic sort of downward continuation that will intersect a phase boundary at a characteristic depth that depends on the phase diagram.
Okay.
And so depending on how you change it, you can get that depth happening at different times. But then
Yes.
the question is, okay, if it's stable against ordinary and diffusive convection, then what is the gradient? So we can't conclusively answer that, but what we can do is place a lower bound on the stable layer thickness. And right at the beginning, this is where I was talking about Jupiter having potentially as few as tens of kilometers
Right.
as the thickness of the stable layer. And the region, the calculation for this is very simple. Basically, we say you can't move the heat with convection, so you have to use radiation or conduction. It
Yep.
turns out that it's a metal, so the optical depth is incredibly thick. So conduction is
Yep.
essentially the only efficient way to transport heat,
Yep.
but it's still not very efficient. And so you have to have basically an extremely steep superadiabatic temperature profile in
Yeah.
order to accommodate the luminosity that we
Yeah.
expect and that we measure on the outsides of these planets.
Okay.
However, it could be thicker because there could be other thermal transport mechanisms that we're not thinking about. As one example, in the Earth, for example, we have a stratosphere, which, as the name implies, is stably stratified.
Yep.
And yet, there is still significant mixing that occurs in the stratosphere. And one example of a mechanism that can cause this to happen is that you have large gravity waves at the tropopause, and these gravity waves, they can break just like gravity waves in the ocean. And
Yes.
when they do, they create all sorts of turbulence, and that drives mixing. So it's not inconceivable that there may be mechanisms like that or other mechanisms that are able to mix up material, even though they're not strictly speaking,
Convective.
convection in the
Yeah.
Rayleigh-Benard sense. They're convection in the advection sense.
Yeah.
That these words are sometimes a little bit ambiguous, but so we just in order to sort of simulate that, we use sort of very loosely the paradigm of eddy diffusivity to talk about it as if it's an enhanced thermal conductivity. And
Yeah.
so we have this 1x, which is a very thin one, and then 10x, 20x.
Got
So
it.
these just are
Got it.
correspond to enhancements in the thermal conductivity that
Got it.
aren't actually enhanced thermal conductivity, but just are meant to model other types of thermal transport mechanisms
Mixings.
that could
Yes.
be at play.
Right.
Um,
What drives the choice of 28.6 and 23.8 on
so these curves are for Jupiter. The 23.8 is the observed helium abundance from so this is capital Y, which is different from lowercase y. So this is a mass mixing ratio
Oh,
instead of
okay.
instead of molar. And
Yeah.
so
Okay.
the outer one is observed. This is also why we focus on Jupiter, because we actually have an anchor point from the Galileo probe
Right.
to let us know how much helium there should be. And the internal boundary is basically under the assumption that the stable layer is infinitesimally thin, which it pretty much is, or
Right.
in the conductive lower limit it is, then just how much helium must there be in the interior in order for the total helium abundance to correspond to the protosolar abundance.
Thank you. I'm with you.
Um, yeah, so these are just, notional, but I think the important thing is that it shows that in principle, the helium rain layer can be very thin. So we compare it against Militzer et al.,
Right.
2022, for example, which shows a helium rain layer extent that extends over a significant fraction of the planetary radius compared to ours, where it's practically infinitesimal.
There you go.
It may as well be a step function, at least from the perspective of interior models. So
Mhm.
this is just to compare and contrast sort of against like the existing state of the art based on the Juno mission of interior models.
Right. Very cool. Okay. I get the point here. Very nice. Mm.
So this brings us back to our original question. We've now made an argument that you can apply equally to both Jupiter and Saturn. So what is the difference? Let's scroll down a little bit on the paper. Let me
Uh-huh.
orient myself. I
We
haven't looked at
got
it
latent
in a
heat
little
and
bit.
stable thickness layers. Then we go into latent heat.
Yes, latent heat. That's the relevant consideration.
Okay.
So the latent heat of the phase separation is something that has been commented on quite a bit by prior works, going all the way back to the 70s from the Stevenson and Saltpeter sort of work. It's also been commented on by Nadine Nettleman. We
Yes.
attempt here to sort of cautiously make a first sort of quantitative estimate that's based on Dave made a quantitative estimate as well, but we're going to try to be a little bit more careful and do a quantitative estimate based on sort of statistical physics.
Okay.
So here we take the latent heat from equation 7. This is just out of a standard statistical physics textbook from
Yep.
Landau and Lifshitz.
Yep.
And it sort of gives you a way to estimate the latent heat that's released when two coexisting fluids, liquids in the case here, but that should roughly apply to the thermodynamic conditions of interest, have sort of a phase separation. So if you
Yes.
imagine you're cooking chicken soup and the fat sort of starts floating out of the top, that process has an associated latent heat, and you can quantify it in this way.
Yes.
And so you'll notice that it essentially requires this KBT, which is fine, and then it requires knowledge of the phase diagram. So because we have this Schottler and Redmer phase diagram,
Yes.
we can
Yes.
again use this to try to estimate the latent heat.
Okay.
And we find latent heat that are on the order of 10 to the 12 ergs per gram.
Yep.
So people might be a little bit surprised to see such a large number, because when you compare it against the latent heat of condensing water, for example, it's about 2 orders of magnitude larger.
Larger.
If you
Yeah.
if you look at the equation 7, you can sort of understand why that difference could be. So ignoring dlny, dlnt, which is part of the detailed behavior of the phase diagrams, if you just
Yep.
look at the kBt over mu term,
Right.
then the temperature environment where this phase separation is happening is about an order of magnitude higher temperature than where water is
Uh-huh.
condensing out,
Yes.
and
Yes.
and then mu, the mean molecular weight, and latent heat is a amount of energy per weight, is also about an order of magnitude smaller for something like
Okay.
hydrogen than it is for
Then
water. And so that's how you get 2 orders of magnitude, assuming that the phase diagram is similar. However, that's not a fully satisfying explanation, because people who think about this stuff a lot know that there's an additional term that actually dominates the water system, which is the change in specific volume,
Yep.
which is not as relevant in this case. So in any case, I would be open to seeing new and more careful estimates of latent heat, especially using ab initio models, for example. So I'm not saying this is the last word on this. We're just trying to give some kind of estimate.
Right.
And but what we find is essentially that if you take this latent heat and you now incorporated it into your calculations of the energy balance for the
Okay.
system,
Okay.
what you find is that for Jupiter, the amount of heat that is transported by latent heat droplets
Okay.
is about an order of magnitude smaller than the amount of heat that needs to be accommodated. So that means that the majority of the heat
Okay.
must still be accommodated by conduction or by some of these other processes.
Right.
And so the arguments that we used apply. However, if you do the same calculation for Saturn,
Right.
you actually find that the latent heat can accommodate basically the same order of magnitude or the entirety of the luminosity that we observe on Saturn.
Yes.
And
Right.
so you no longer necessarily need to transport large quantities of heat using other mechanisms. The rain can accommodate
Does it
basically
all.
all of it. And so this brings us back to figure 6,
Figure six. Yep. And
where we can sort of make sense of where these differences arise from.
I have better intuition on these. Okay. Hmm.
An essential part of this is really what is the difference between Jupiter and Saturn? The short answer is, well, they have different masses. And because they have different masses, they reach the pressure level at which hydrogen-helium phase separation occurs at different depths.
Yes.
And because they reach it at different depths, that
Yes.
means that for Jupiter, it's a relatively small fraction of its total mass that's above the helium rain layer, whereas
Uh-huh.
on Saturn, it's a large fraction of its total mass that's above the helium rain layer. And
Right.
so if you want to increment the temperature down, infinitesimally on either planet,
Yeah.
then you are going to create some helium raindrops. But in order to accommodate the entire helium budget of that whole envelope,
Right.
for Jupiter, it's a relatively small fraction of its total mass that needs to be accommodated. So you can think of it like in this picture of relatively sparse, gentle helium rains falling
Right.
compared to Saturn, where you need to accommodate a much larger fraction of the planet's mass to have all that helium transport through that stable layer.
It's a
And so
downpour.
instead, you will have a much denser, sort of more torrential
Right. It's a downpour.
flux of helium rain. And it turns out that that additional flux is able to accommodate
I'll make the
Saturn's
like heat.
luminosity.
Yeah. 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 Very cool.
So that's the basic theoretical argument. Maybe it'd be a good idea to briefly go through the conclusions,
Yeah.
and
Sure.
then that's about it.
Okay. Conclusions. Let's walk through what we got out of this. Okay.
So they're numbered here. So the effective coefficient of thermal expansion that we talked about is negative
Yes.
in the relevant region. So we think
Yes.
it's stable against both ordinary and diffusive convection. The lower limit for stable thickness is very thin compared to the radii of the planets.
Sure.
Although a thicker stable region can't be excluded, but we can place a lower limit on how thick it should be. And then the latent heat should be on the order of 2 times 10 to the 12 ergs per gram with significant uncertainty. And so the latent heat flux associated with this rain is
Yes.
sufficient to accommodate Saturn's luminosity, but not Jupiter's. And this could explain the differences between their external magnetic fields.
Right.
Um,
Right.
and so that's basically what comment 4 is about the magnetic field, which we can talk more about. And then I also just mentioned, just because I also do some work. I think the last one we talked about was about seismology. So, but we
Right.
just note that these are stably stratified layers, and they can host internal gravity waves
Yep.
that are
Yep.
relevant to Jupiter and Saturn seismic spectra. So,
Yep.
as we continue to study the seismology of these planets, that could be, in addition to magnetic fields, a good way to sort of get at empirically how
Yes.
we expect these stable layers to be behaving.
Uh-huh. Very nice. Beautiful. 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 Steve, I want to thank you so much for walking us through your very awesome article on helium rain. Very nice.
Yeah, thanks for taking the time.
Sure. And you kind of touched on it a couple of points there as we went through some of the various uncertainties and whatnot. And so let me push on it a little bit and ask, Where do you think we go from here given the published article? Is there additional experimental work that should be done? There's always more theoretical, especially EOS work to do. But just sort of next steps. Where do you think we go from here on the topic?
Yeah, I certainly think that laboratory measurements, not just for this, but for a wide variety of applications to the interior of giant planets,
Mhm.
are going to be important.
Okay,
I would, if you are a high pressure physicist that stumbled upon this video somehow, please,
get in touch.
let's talk about what laboratory resources you might have and how we might be able to use this to help get a better handle on the equation of state empirically, which is
Yes.
obviously the gold standard in science. Additional computational and theoretical work is also very much warranted. In general, as someone who is a little bit outside of the field of, or a lot outside of the field of this ab initio quantum mechanical simulations,
Yeah.
I'd like to see a consensus over
Fair
what we
enough.
really think the phase diagram should be sort of
Fair enough.
materialize over the coming years. And then for work that I am personally interested in working on, I uh, I think that this issue of the magnetic field can be instructive. So sort of the one of the prevailing theories for why there is for why Saturn has such an axisymmetric magnetic field is because if you have a layer of stable stratification above a magnetic field. So Dave Stevenson did this in 1982. If you imagine sort of in Cartesian coordinates that you have some sort of variable magnetic field, and then over the top of it you have a electrically conducting conveyor belt that's going over the top of it. So then from the perspective of this conveyor belt, it's experiencing a time-dependent magnetic field.
Yes.
And then, so from Maxwell's equations, this is going to drive currents in the conductor, and these currents are going to generate their own magnetic fields that countervail the underlying magnetic fields
Okay.
and attenuate them.
Okay.
So the idea with Saturn is that you have this helium rain happening, and this leads to a layer of static stability that is going rotating over the top of the dynamo, and this axisymmetrizes the field because only the components that do not have any
Yes.
time dependence from the perspective of the rotating shell are going to survive that attenuation process.
Cool.
And so in Dave's original article from the 80s, he suggested that perhaps Saturn is undergoing this phase separation and Jupiter is not, and that explains the differences between their magnetic fields. Um, However, as the Galileo probe sort of threw a wrench a little bit into that explanation because it said, well, no, this phase separation is happening in both planets. So why is the same thing not happening in both planets? So my prediction is that something similar actually is going on in Jupiter's magnetic field, and I've started looking into it preliminarily. And I'm not sure yet because I haven't done a lot of stuff with magnetic fields before, but I think I am seeing that there is some type of attenuation, not to give too much away. And so the idea is that you can use the observations from the Juno mission in order to constrain what the thickness of the stable layer and depth of the stable layer might be. And those constraints might then be able to be used to put constraints on the phase diagram. So
Yes.
we can maybe like learn something about quantum mechanics by studying Jupiter's magnetic field. So that's another exciting potential future application. And I want to mention one more because one thing I'm noticing, especially with exoplanets and with other planets in the outer solar system, is that what the theory that originated with Tristan that was supposed to apply to volatiles in an atmosphere.
Okay. Sure.
It apparently is applying to more and more situations. So a couple of years ago, we wrote an article about how it might affect sub-Neptune, super-Earth exoplanets.
Okay.
The hydrogen-helium system, I was skeptical of until I did the calculation that it was a relevant factor for that. And so as we begin to get more data about how hydrogen interacts with other elements like water and rocks, we can begin to do similar calculations for other bodies. So
Yes.
Uranus and Neptune and
Well,
exoplanets, where this might be a relevant consideration.
mhm.
So essentially, you can take this equation and just plug in the phase diagrams and do it for any sort of
Yeah.
coexisting phase separating system and see what you get. And if you get a negative coefficient of thermal expansion, in
You're
each case,
good.
it could really change the way that we think about these
Yeah.
planets really behaving.
Yeah. I hadn't actually thought about that. It's very cool. Very nice. Well, it'll be really exciting to see this develop over the next couple of years. especially you experimentalists out there. Yeah, I have to agree. If you got three different independent groups doing ostensibly the same calculation, it would be nice if they got within some delta of each other as opposed to orders of magnitude. So, yeah, it'd be very cool.
Indeed.
Yeah,
The difficulty is though, that doing the calculation exactly is computationally
challenging.
impossible or impractical. And so you always have to invoke some sorts of approximations.
Mhm.
And I guess what we found is that different types of approximations actually do yield substantively different results.
Right.
And none of those results are in agreement with the experimental results. So I
Uh-oh.
mean,
Science to the
I won't
rescue.
pretend to understand the specific sources of these discrepancies, but I do hope to see some resolution in the upcoming years.
Very cool. Nice. And that will do. And I hope this made your astronomy day, your helium rain day, just a little bit better on this January 9th of 2025. And we will see you on the next one.
All
Bye-bye.
right, thank you very much.
Yeah.